So the thing is, the problem that I have in this class on an ongoing basis is continuity, because there are people in the class who have been here for 11 years, and there are people in the class who have only been here today for the first time. And there are people who have just come for the last few weeks. And so the ongoing topic has to always somehow refer to, although it refers to things that I've talked about before, it again has to always be new and in fact an introduction to astronomy, which is exactly what I did last week. I did an introduction to astronomy, and you would think that that would be enough, but in fact, some of you have not had that introduction. Anyway, today I'm going to do, if you will, another sort of introduction to astronomy, but from a different point of view. What I want to do, see, the ongoing story that I'm telling, despite the fact that there's hardly anybody in the room who's hearing my story, is I want to tell you the story of how big the universe is. That's my story. Come for the story of how big the universe is. And I will tell you that same story every week in different fashions. So though you may have missed the story from last week, this week's story is going to be also an explanation of how big the universe is. So that's not the universe over here. That's the Milky Way, right? You've seen the Milky Way in the sky, but mostly you haven't, because if you live in New York City, you don't get to see the Milky Way because the lights are too bright. If you live in the northern hemisphere, you don't get to see the Milky Way because it's really the cool part, this part right here, you can only see from the southern hemisphere. So in order to really go to get the Milky Way as an incredible sight, you need to have a vast horizon, and you need to be south of the equator. And I've had both, and I can tell you, they call this the backbone in the sky, and it is fantastic. When Galileo pointed his telescope, because he didn't just point his telescope at Jupiter and get the Galilean satellites named after him, the four of them, that are visible only through a telescope, although somewhat via the naked eye. You can actually, if you have an acute eye, you can see the moons of Jupiter with your naked eye. But he turned his telescope on the Milky Way, and he discovered that the Milky Way had stars in it. The stars are unresolved, but with a telescope you can see them. You can see the stars in the sky. There's a place in the sky to look. How many of you have seen the Pleiades? How many of you have seen the Pleiades? Yeah, you've actually. Now, the interesting thing about the Pleiades is they look like a itty bitty Big Dipper in the sky. It's like, ooh, they shrunk the Big Dipper, and it's a teeny little thing over there, and yet you count those stars, and you naked eye you'll count more or less 6, although the Pleiades is often referred to as the 7 sisters, so there's at least a 7th, but there's actually 9 that you can see with your naked eye if you happen to be an expert shepherd. But if you look really hard, you can see even more if you happen to have a telescope. So let's see. So this is the Pleiades. The Pleiades looks, well, we can count 7 stars. 1, 2, 3, 4, 5, 6. We can count 6. I guess that's a 7th. Some people can see 9. They can't see this nebulosity here. That you could only see in a telescope, and in fact you could only see it with a camera that draws and integrates the light over a period of a few seconds, so that you can get to see this nebulosity. When I look at it through a telescope, I don't see that. I just see the stars. And it's one of the few things I've ever looked at in a telescope. And the reason is you can find it in the sky. I want to find it. This is what I know about the sky. I know very little about the sky. Extremely little about the sky. When I look up in the sky, and when I look to the south from my country house, I see, standing right down the road that passes in front of my house, I can see Orion. And Orion, although this looks small, Orion just is big in the sky. It's really big in the sky. And I don't know the sky, so when I look around, I don't know where the Pleiades are. But this picture will remind me that it's over there, kind of like where his arrow or his bow and arrow are pointing. And there's the Pleiades. So what I can do is I can come and I can zoom in and see what the Pleiades looks like. See, it looks like a little dipper. Pleiades is nearby. Pleiades is about 130 light years away. What's a light year? A light year, that's insane. First of all, the idea of a light year makes the word light year is a confusing word, because people don't get that. They think of it more as a time rather than a distance, because it ends with the word year. So, but a light year is the distance that light travels in a year. How many of you, I certainly am among the people who sat down one day to figure out, once you learned how to multiply, how big a light year is? How many of you ever sat down and calculated it? There's he owned a telescope as a kid, and here first you're new to the class, and yet you calculated a light year. So, and nobody else did. Oh, I assume somebody else did, but I'm the only. I calculated a light year. Let's calculate a light year. So there's a calculation of a light year on the screen. What you do is, you know the speed of light, 186,000 miles per second. You multiply that by 60 seconds. You multiply that by 60 minutes in a day. You multiply by that by 24 hours in a day. And then you multiply that by 365 and a quarter days in a year. And you come up with a number that is almost exactly, but not quite exactly, 6 trillion miles. 6 trillion miles. That's a big number. And yet, because you can't conceive of it. Okay, how about this? The light can travel around the Earth 7.5 times in 1 second. That's what Superman has to do if he's going to travel back in time. He has to go in the opposite direction the Earth spins 7.5 times in 1 second, and if he does that fast enough, he'll be able to go back in time, and that at least is how he did it in the first Superman movie. And also in the comics, if you know the comics as well. Of course, that doesn't work, you know that. But nevertheless, 7.5 times around the Earth in 1 second is the speed of light. It takes over a whole second to get to the moon. And hours to get to the planets. It takes something like 10 or 20 hours, I forget, for light to get to Neptune. Size of our solar system is let's say, ends at Neptune. Let's say that's completely not true, but for the purposes of childlike observations and thought about the solar system ends at Neptune. Let's imagine that Neptune, the orbit of Neptune, represents a circle whose size is a quarter. 1/4. How big do you think the Milky Way is? How big do you think the Milky Way is if the size of the solar system is a quarter? I'm going to ask you for a reasonable guess. If anybody has a guess, okay, is willing to take a chance that I'm going to make fun of it. Who wants to take a guess? Because you could go wild and go something crazy. I'll suggest this is a quarter. It's the size of our solar system. What's the size of the Milky Way in comparison? If you laid it down on the ground, how big an object would the Milky Way have to be in comparison? Anybody? Nobody's willing to take a risk. That's fair. You know me better than that. Okay, you know me that I will make fun of you.
You can't pronounce it, whatever it is.
No, I'm saying is there is an object well known to you, okay, that it has the same ratio as this quarter is to that as the orbit of Neptune is to the Milky Way. It's a ratio, okay? 6th grade math. What is the missing x, the object, in that ratio? What is the x that would make the ratio perfect? The quarter is to x as the diameter of the solar system is to the Milky Way. What is x? Anybody? Still nobody. Okay, that's fair. X is the continental United States. The continental United States is to the orbit of Neptune the continental United States is to a quarter as the Milky Way is to the orbit of Neptune. By way of saying that you cannot even get your hands around in any way, shape, or form how big the Milky Way is. But that is the subject of today's lecture, more or less. The Milky Way is a big place. And the whole idea in this class is to figure out how big a place is the universe. But that's, of course, an absurd conversation if you can't get your heads around the size of the Milky Way in the first place. And although this ratio certainly should have helped, it's really an impossibility. Now, for those people who just, and there are now, I think, 2 or 3 people, of the people in this room, about 4 of you, 2 of you are never been here before. A total of 3 of you have only been here 3 or 4 times. And so for those of you, you need to know that you can ask questions at any time, okay? That's the point of this class. That's what makes the class work. Okay. Otherwise, I'm just lecturing, you know? So how big is the Milky Way? Well, that was a question that certainly had been asked in the past. For one thing, around 1920, they had it pretty well down that the Milky Way was the universe. So that's everything you see in the sky. That's it. Nothing else. That's the universe. They have these things called nebulosities, which they can see. These naked eye things you can see, and they just call those nebula, and they belonged to the Milky Way clearly, and other nebula that they saw in the sky, none of which shows up here. maybe there's one over there. Let's see, maybe that nebula right there. Because I don't know where these things are in the sky. That, or that, or that. They all belong to the Milky Way in 1920. But after that, they got to live an external existence outside the Milky Way as they discovered that the Milky Way was just one nebula in the universe. And now, of course, we call it a galaxy. But there are other galaxies in the universe. And we will and we have talked about the galaxies in the universe. But this is our galaxy, and we know nothing about it. Yes?
I have a question of perspective. If our solar system is within the Milky Way, how does that view, how do you derive that view which looks like it's from outside the Milky Way?
Well, this view is actually the sky. Right now, this is our sky. This is a picture that you can take. It's actually more than our sky. It's a little bit. This is more than 180 degrees of sky. But nevertheless, you can take this picture with a camera south of the equator. What is your question?
My question is, if we're part of that, how do you get the picture that appears to be from outside of it?
How do you get a picture of the Milky Way that appears to be outside of it?
Because that's what that is, right?
No, this is the picture of it with us inside of it. This is the sky. This is the sky overhead tonight. It looks like this. It's just only a portion of it. Do you see? If you take a picture and you add up all the pictures as you walk around the Earth, you can take this picture. It's the picture of the Milky Way from inside. That's actually not your question, I don't think. Because what you've seen pictures of the Milky Way from the outside, and this is not that one. The picture of the Milky Way from the outside, I will show you a picture of the Milky Way from the outside. So this is a picture of the Milky Way from the outside. Now, same question. How did they get this picture of the Milky Way from the outside?
Exactly, where's the camera?
Where is the camera?
It's in a phone booth.
So the answer to that is always the same. This is not the Milky Way. This is another galaxy that is thought to look like our Milky Way. So while we can't take anything like a picture of this from inside the Milky Way, the only picture we could have taken was this one that we just saw. That one. We live in the plane of the galaxy.
That's the answer to my. This is a horizontal view, and we're looking at the flat part of it.
Right.
And we're in that flat.
We're in the plane of the galaxy. We lie along this plane.
Right.
And so this plane, so this area here blocks our view. This entire area blocks our view of the sky, which you do see above and below. But through here, you can't see anything. Anytime you take pictures of the universe, you end up pictures of the universe, and there's something missing because this is blocking our view. So all pictures of the universe look like a butterfly with something missing, a dark area where the Milky Way lies. So we have the Milky Way in that picture, but if you want to see the rest of the universe, you have to take the Milky Way out. The Milky Way is, so we don't really know what the Milky Way looks like. What I do when I do this, I actually cut out this time in which I'm looking for something now in my videos. For those of you who don't know, I make videos of this class, and it's on the web. And there are over 35 of these classes on the web. And although this class right now is about 20 people, there are 250 people who are also in the class, who are on the web. They watch. They don't stay as long as you, but they watch. So this is the Milky Way as far as we know it. It's a drawing. And what do we have? We have, this is the galactic center here. This is us right here, which is why all the lines emanate from us. And this is the spiral arms of the Milky Way. Follow this one. Follow this, and it's dotted because you can't see through the galactic center. And then you can pick up and you can see that the spiral arm continues around until it gets blocked by the galaxy and the light. So that's the blue arm, which is called, I don't know, the Perseus arm. There's an outer arm that goes like this. There's an inner arm that goes like this. And I guess it's called the Sagittarius arm, but I really don't know. Okay, and then there's even, there's 4 arms that are supposedly make up the Milky Way. There's a 5th arm right here. And it's called the Orion Cygnus arm. And it's a teeny itty bitty arm that doesn't seem to be related to the rest of the Milky Way. And so, because it happens to be close to us, we can see this arm well, so we know we're lying on some sort of arm, but we don't really see it continuing around. So maybe this is just a broken fragment of an arm. Yes?
Is there some theory why it's in a spiral?
Say the question again?
Theory.
Is there a theory of why it's a spiral?
Why it's a spiral. Or you were pointing, I thought, to other ones that are
Yeah.
also in a spiral.
There are 3 kinds of galaxies. There are basically 3 kinds of galaxies. There are spiral galaxies, there are elliptical galaxies, which have no spiral structure, and then there are irregular galaxies, which are neither of those. They just look jumbled up. So why does the universe come up with a spiral galaxy? Truth is, I can't tell you in this lecture, because it's complicated, and it will be at some point in the future a lecture of mine. All I can say is, if you spin something around like a pizza, and you put tomato sauce on the pizza, and then you spin it, you're going to get a spiral sort of thing going on too, right? That would make sense. So think of it as the galaxy being a pizza which spins up, and so things trail behind. Okay, that's not a good enough explanation by any means. But the explanation, on the other hand, is not simple, and I know that. So I can't actually answer your question in a reasonable fashion, except to say it's the norm. It happens all the time. Many, many galaxies. And one of the things that I do this class, I've been doing this class for 11 years. One of these classes will be, I'm going to show you 100 galaxies and 100 spiral galaxies. And they're all different and they're all beautiful. And then when I do that conversation, I'm going to explain why. But up to this point, I'm not feeling qualified to do that. I do a lot of learning for the class, and I can usually answer questions, but this one I can't, because it's hard. Okay? I can tell you this, though. It is a wave phenomenon. It's not a simple aggregation of stars in a spiral. It's a wave that moves around the galaxy and creates the spiral structure that you see in the wave. At some point, the wave will move elsewhere and the spiral will have moved. So that's something. But more I can't say. But,
So
yes.
what exactly are the arms made of?
Okay, that's a good thing. They're mostly made of stars and gas. The gas is forming stars. The stars are busy burning the gas and churning the gas and exploding the gas and sending it back out into the universe, into the galaxy, where they can be reformed again into new stars. So there's a constant churning of stars into gas, into stars. Mostly stars. Mostly stars. Some clouds of stars. Clouds of gas.
in between the arms is just empty space?
Well, let's put it this way. The Milky Way is mostly empty space. Okay, really empty space. I mean, you go from here to Alpha Centauri, which is the nearest star. You're not going to meet anything along the way. You're going to travel for 100,000 years at conventional speeds to get to the nearest star. Empty space the whole way. Nevertheless, if you think of that area, we're in a spiral arm. That spiral arm has gas. So as you pull out far enough, you'd see the gas. But the gas is at the concentration. There's 10 to the 23rd atoms in this cubic inch of space in this room. In outer space, there's just 10 in this cubic inch of space. So if you pull out far enough, all of that 10 plus 10 plus 10 plus 10 adds up to a lot of gas. But you have to take a lot of space in before you can get all the gas that we're talking about. But the stars are far away, so they have a lot of, have a percentage of the gas. Not all of it, some of it. Yes, you.
Isn't some of it also dark matter, as the Jewish astronomer who just was named down in South America, the first Jewish astronomer?
None of it is dark matter.
None of it is dark matter?
No. Now, how can I say that? Dark matter is really famous, okay? We know that the dark matter makes up most of the universe, most of the matter in the universe. You know, in terms of matter, it makes up 75% of, no, 90% of all the matter in the universe. And yet, I told you that between here and the nearest star, there's no dark matter. That seems insane. And the reason is because dark matter is diffuse, and the stars, we're talking about a small distance between here and the nearest star. We didn't go far enough. If you have to, we went 4 light years. 40 light years? No. How about 400 light years? Not good enough. How about 4,000 light years? Still not good enough. How about 40,000 light years? Now we're talking. We're surrounded by dark matter because it's everywhere, but it's not concentrated. So yeah, there's some dark matter in my hand right now. There's more air in my hand right now. So that the dark matter doesn't count. It's only when you go to the entire Milky Way and say, look, I got a Milky Way. What is it made of? The answer to that is, well, mostly dark matter. Some stars, mostly dark matter. But not here. Not here. It's mostly air. Mostly this. It's not dark matter. So dark matter doesn't come in until you start to talk about galaxies. Up to that point, it's not a conversation. Okay. So the thing is that the story that I want, one other story I'd like to just tell quickly is, we talked about what a light year is. This is a list of light years sort of things. So just in terms of how far away things are, okay? The moon is a light second away. The sun is 8 light minutes away. The spacecraft that we sent beyond the edge of the solar system, called New Horizons, is 4 light hours away. The furthest spacecraft we've ever sent, and it's still sending back signals, is 20 light hours away. We're not even at a light day. And then, of course, the sun has maybe it's 2 light years. It owns about 2 light years worth of space. but the nearest star is 4 light years. Center of the galaxy is about 50,000 light years away. 50,000. And we have 400 billion stars in that, 400 billion, and yet there's as many galaxies in the universe as there are stars in our Milky Way, and then some. That's just comparison. So, universe is a big place. I want to do. Okay, so what we really want to know to get a sense of stuff, in order to understand what's going on in the universe, you need to do two things. You need to do space and you need to do time. And you are all amateurs when it comes to space and time. You live in your little space and you live in your little time. And what you need to do is to live in a bigger space. Because I think the whole idea of this course, in fact, is to make you small. Because the smaller you get, the more you can appreciate the fact that your time on this earth and your space on this earth is just, is so fleeting that if you really want to get your mind big before you leave this place, you need to put yourself not only in space and expand the space that you live in, but you need to also expand the time that you live in. It's very hard. One of my favorite ways of expanding the time I live in, I used to have a parrot. Parrot lived on my shoulder for 15 years. Me and Frobisher. Frobisher lived on my shoulder. And the thing about Frobisher is that we had a lot of things in common. We loved each other, for one thing. But Frobisher and I also had another thing in common. We had a common ancestor. We had a common ancestor, and that common ancestor maybe, I'm going to say, 100 million years ago. Frobisher and I had a common ancestor. And that's really interesting. You work that for a while, and you try to think about how much 100 million years is, and how nature could have evolved so that he and I could be related. That does help bring you a little bit space and time. 100 million years is a good place to start, because you can at least, I can look at Frobisher and say, hey, you know, we're cousins. But that's only 100 million years. You need longer than that in order to appreciate the universe. Can somebody go in the back room and close the door back there? Thanks. So the universe is 13 billion years old. I'm only doing 100 million. The Earth is 4 billion years old. That's 4,000 million years old. Frobisher and I had only 100 million years to share a common ancestor. There is a spacecraft that was launched a few years ago, 1980s something, that tried to answer the question, what does the Milky Way look like? You see, the Milky Way is two-dimensional. And no matter how hard you stare at it, it's still two-dimensional. What you got to do is you got to stare at it for a while, and you got to use really cool instruments that can stare at it and say, aha, I know where that thing is and I know where it's going. I can see that star, and it's yay far away, and it's going this way. And it used to be there. I'd like to know not only where things are, but when they are, where they're going, what their mission is. Because if I can begin to understand stars one at a time and then group them together, I can begin to understand the Milky Way itself. It's not just a set of stars, it's a history. The Milky Way has a history. And it has things that are bright, could be far away, things that are dim, could be close. I want to know where all those things are in the sky. You've got to build a satellite to do that. And they did. They built a satellite called HIPPARCOS. and it was launched, and it did a good job, and it finished its job a few decades ago. And since then, there have been only one other spacecraft that was designed to do what HIPPARCOS did. I'm going to show you what HIPPARCOS did. I'm going to show you what GAIA, the latest spacecraft, did. So this is a YouTube video. Okay, so this is GAIA. I mean, this is HIPPARCOS here. This is GAIA there. Now, right here, what you're seeing is the stars that it saw. This is not a cute little picture. This is a picture with real stars, the stars that HIPPARCOS was able to catalog, the stars that GAIA was able to catalog. And we're just simply going to pull out from wherever that is. That's the sun. You can see the sky is brighter. GAIA saw more. And as we pull out even further, you see GAIA is hardly seeing anything anymore, but HIPPARCOS is still seeing stuff. Now, you see the stars moving because we're moving back through the galaxy, through the same data, except one is 10, 20-year-old data, and this was this year's data. This year's data. You see HIPPARCOS, not so much. GAIA, a lot. And we pull back, and there's the Milky Way like no one has ever seen it. No one's ever seen the Milky Way, right? Because you can't take that picture. So this is not the Milky Way. This is a picture that somebody thinks this is an artist's conception of a Milky Way. Or this is a picture of another galaxy that we think looks like the Milky Way. So this is not the Milky Way, but this is the Milky Way, nevertheless. This is what HIPPARCOS could see. This is what GAIA could see. GAIA can only see 1/100th of the stars in the Milky Way because, well, it was, this could see hardly anything, okay? This can see to the center of the galaxy. It can see all sorts of stuff around the galaxy. We know so much more as of this year when the second, they call it DR2, that means GAIA Data Release 2. When there was a moment in time in which somebody pressed a button and all the data that GAIA had gathered for the last 5 years was dropped on the internet. And you can believe 1,000 astronomers went crazy with the data. Lots of people went crazy with the data. We know a lot more about our Milky Way now than we did last year at this time. What are some of the cool things? Well, I think one of the cool things is that we know where the stars are now and where they're going. So I think what we should do is look at some stars. This is stars in the sky. The number that you see at the bottom moving is time. 200,000 years ago, 200,000 years from now. Stars. What I want you to do is to have a good time with that picture. And right now you're not having as good of a time. Why? Because I want you to see this picture in 3 dimensions. And for you, right now you're seeing two-dimensional pictures. I want you to see one 3-dimensional picture. In order to do that, I'm going to ask you all to cross your eyes and play a game with me that is a good game to learn to play in life. It's how to see how to take two pictures that are taken stereoscopically of something and turn them into a single picture that you will see in 3 dimensions. How many of you have ever done that trick before? 1, 2, 3, 4. Okay, there's about 20 of you in the room. We're going to try this. If for those of you who try this, most of you will fail. Some of you will not. But it's a fun project. So here we go. So I'm going to first tell you how to do it, and then I'm going to ask you to do it as well. See my finger? If I hold your finger up in front of your face, okay? And look at your finger. And as you're looking at your finger, you realize that the people behind your finger are out of focus, and they're not where they're supposed to be. As soon as you look at the people behind your finger becomes 2. You have 2 fingers. I'm looking now at the rest of you. I'm not looking at my finger. I have 2 fingers. When I look at my finger, then you become doubled. Each eye is looking. What I want you to do is to look at your finger in such a way that these 2 move together and become one. When you're looking at your finger, you're going to see 3 pictures. You're going to see picture 1 on one side, you're going to see picture 2 on the other side, and you're going to see a third thing in the middle. And that third thing is the stereoscopic version of these 2. The problem is, that's easy. The problem is, as soon as you try to look at the third picture, the one in the middle, it disappears. Or it goes, because your eyes, when you try to focus on this, will automatically change and refocus and do all sorts of crazy things. You have to find a way for your finger moving back and forth in line to just be in the same place as that third picture, and then without moving your eyes, refocus not on your finger but on the third picture behind you. That's hard. You've got to focus on the third picture while not shifting your eyes, because your eyes will go parallel. You have to keep them crossed. You have to keep them crossed as you look out, and just change the focus, but not the cross-eyed. If you achieve looking at the third picture without uncrossing your eyes and just focusing on the third picture, you will see it in 3D, and it will pop out at you. Since this may be not as encouraging to do this, we'll come back to this. I'm going to give you some other pictures to look at. You've seen this. You've seen stereopticons. How about a picture of a monster? Okay, same thing. See if you can do it with a monster. Anybody having a success that never did it before?
I get it, but for a split second.
For a split second. There we go. Okay, so there it is. You now know it's possible. Now it's a matter of practice. Now it's a matter of practice. And, yes?
3D movies is on that basis.
No, 3D movies is on the basis of each of your eyes is seeing a different image, but you don't have to cross them.
Right, but it does combine and coalesce them and make it into one image.
Yes.
That is 3D.
Right, but you don't have to do the pain. No pain.
Easier.
Easier. This is very hard, but it's worthwhile because there is a world of 3D out there that is available to you on the web to show you all sorts of cute things. I mean, this is just one website. This is people having dinner. This is a bug. This one, that's not interesting. This is a great one. I love this one. This is a battleship from, I guess, around around the Civil War. Keep trying.
Escher also. I mean the painter.
Yeah, Escher.
When you focus on his work, you don't have to go cross-eyed, but it does.
Escher's work is spectacular, but it isn't this. He never did this.
No, but
He does perspective.
Right. But
He does perspective, and he does it amazing. Okay, well, did you see it? Oh, no, she didn't see it. Okay. Well, I tried. I tried. The point, obviously, of what I was trying to do was to give you a sense of. Now let's go back to this and let you guys try one more time to do this. Because if you can do it, what you're seeing is 400,000 years worth of data showing you how some stars in the sky, specifically the Pleiades, move. Because the Pleiades is made up of thousands of stars, not just 7, not just 6. And because it's close, what Gaia did that was remarkable, Gaia was able to see things that no instrument has ever seen before. Gaia was able to see something move the width of a human hair from a distance of 1,000 kilometers. That's how accurate that satellite was. It was able to see movement in the sky of a human hair if that human hair had been placed 1,000 kilometers away. So the stars in the sky are moving, but they move very slowly because it takes thousands of years for them to see, for their movement to be seen. Nevertheless, they can be seen if the instrument is powerful enough. They made an application based upon the idea that I've got all this data, I know where things are, I know which direction they're going in, I can take any star in the sky that Gaia has seen, among the billion stars or so that it has seen, it's seen millions that they know where they are and where they're going, and I can take those stars and I can make them move, any star make them move. In particular, there's a Little Dipper, okay. So where's the Big Dipper? There's the Big Dipper. Okay, I'm going to leave the Earth in this picture because, and what I'm just going to do is I'm going to move time. I'm going to move time. So the way I move time is I press play, and then I press a button on this keyboard. And every time I press a button, time doubles. So the Earth will start to spin faster and faster. And now the years are passing faster and faster. Still 2020. Now it's 2000, still 2020. It's 2021. 2023, 2027, 2040, 2100, 2200, 2800.
It's moving in two directions.
3,000. 7,000. 17,000. And you can see the Big Dipper has changed its shape and no longer looks like the Big Dipper. Do you see that? Do you all see that? There's the Big Dipper. Let me just put it back in time. There it is again. The time is 3,600, 40,000, 47,000, 53,000, 60,000 years, 70,000 years, 82,000 years. One of the reasons and the stars in the sky are moving as well. You see them moving? They're not just twinkling, they're moving. You see that? The stars move, but it takes, you have to be alive for 100,000 years to see this happening. You are getting the benefit of living 100,000 years into the future in this room right now. The world, you're not going to see the world change. You won't know what happens in the future, but I can guarantee you that this will happen in the future. No one is ever going to be able to tell you what the future is like, but this is the future of the sky that you live below. I will have on my gravestone, I've already set this up. On my gravestone it will say, I know I'm dead, but I'm still curious, tell me what I missed. That's what I put that there. This is not enough, okay? I want people to come by my gravestone and tell me what I missed, okay? There's a lot of things I'm curious about. I certainly like to know the next 10 years worth of what the iPhone is going to look like. I certainly am interested in whether they're going to ever discover life on Mars or on other planets. If we survive as a human race, I think we will at some point discover whether life is ordinary or extraordinary. Come by and explain it to me. Nevertheless, this is true. And this I can know now. So, if you ever needed to know what the world is like, this is it.
How do you know that? How do we know this now?
How do we know what?
How do we know this now?
Okay, that's the right question. How do we know this now? And the reason is because Gaia Data Release 2, gave us the position and velocities of over close to 1 billion stars, of which these are a few. Not only did it give us its movement across the sky like this, it also gave us the movement across the sky like this. And you combine this with that, and you get direction. You get horizontal and vertical and at you, and they know exactly where the stars are headed.
Right, but you're assuming the same movement over time.
Not assuming.
No. Right.
Gravity, we know exactly about gravity. Einstein, Newton, we know gravity. If you can literally take any of these billion objects, and you know all the gravity around them because you see there's 1 billion objects. You add a little bit of gravity there, a little bit of gravity there, a little bit of gravity there, and you put it into a computer and you say, go. Oh, and you also add not just that, but where they are and how fast they're going. And you ask a computer to do that, and it knows exactly where it's going to go. And you know what? If something's going this way, chances are it's going to go that way for a very long time. For example, the sun, our sun, is going that way, okay, let's say. And it's going to go that way pretty much in a straight line for a very, very long time. But you know what? After 150 million years, our sun is going to be back here again, going that way again, right from here, because our sun's going around the galaxy once over every 250 million years. But I'm only talking about 1 million years. So in sense of 1 million years, the thing is just going that way. I only showed you 100,000 years. So it's going that way because the orbit, and they're all going around the galaxy, is going to happen in a much longer period of time than the little movie I just showed you. Barbara, did you have a question?
Yeah, I guess that's a very short time. And with the perspective of the universe, but might anything happen in that time, like a supernova or something unexpected that might change that?
Well, okay, might anything happen in this short time that might change it? So let's say that Betelgeuse blows up right now, okay? How does that change the orbit of the sun around the galaxy? Not at all. Just one star. It's 700 light years away. It may lose some of its stuff, but even if it loses its stuff, when Betelgeuse blows up and becomes a supernova, which it will in the next 100,000 years, its stuff will still be 700 light years from here and still have the same gravity. So although it's more diffuse, Betelgeuse will still have this exactly same influence on us gravitationally as it does now, even after it blows up. Because the gases don't get far enough away. They stay there. And so they'll stay there. The only thing it could possibly, if the sun blew up, okay, that would make a difference. If Alpha Centauri blew up, the nearest star, nothing. It would take our sun blowing up for anything to change where we're going and how fast we're going. So nothing. There's nothing going to happen that's going to change the story that I just told. The stars blow up all the time. Gaia itself expects to find thousands and thousands of stars blowing up while it's watching, because it's watching not just the Milky Way, where one or two might blow up every 100 years or so. It's watching all the Milky Ways out there, and all the Milky Ways. It's watching a billion galaxies, and if you're looking at a billion galaxies, and if they pop off every 100 years or so in a galaxy, then you can see thousands and thousands of supernovae. They'll see that change, nothing else. So you want to try that again? No, we'll leave it.
So what
Yes.
are we seeing there? The movement is time. How do they get the movement of those, I guess, stars?
Yeah. How did they get the move? Well, how did they get the movement of those stars?
Yeah. Was it an extrapolation of something?
If you know, yes, exactly. It's extrapolation. If you know how fast I'm going and where I started from, you will know where I'm going and when I'll get there. And you can literally create a cartoon of me getting there.
So it's an extrapolation over how much time to get that much movement.
The picture you saw of the double,
Yes.
that was 400,000 years, 200,000 on either side. 200,000 in the past, 200,000 in the future. Yes.
So what we saw was pretty clear to me that the constellations, which started out in the beginning of the frame as constellations, you could see, Orion and this one and that one and Aries, but then as you moved ahead in time, the lines became extended because that was 70,000 years.
Yes.
And then you saw all the lines go into the overextended lines of what time would
Right.
ring, would right.